Hi guys, welcome to my channel. Imagine you are building a model to predict whether a company is likely to default. You start with 5 variables: profit, leverage, interest coverage, liquidity, and cash flow. The model works reasonably well. Then you think, why stop at 5? You add 20 more variables, then 50 and 100. Macroeconomic variable, market price, credit spread, accounting ratio, and so on. And eventually something strange happens. Your model becomes better at explaining the historical data, but worse at predicting the future. This is one of the fundamental problems machine learning tries to solve. In finance, we are rarely interested in explaining yesterday perfectly. We want to make better decisions tomorrow. So today, we're going to build a practical framework for 6 major supervised machine learning techniques: penalized regressions, support vector machines, K nearest neighbors classification and regression tree, ensemble learning, and random forest. These models look different on the surface, but they are all trying to solve the same fundamental problem. Before we look at the individual algorithm, we need to understand the problem they are designed to address. The problem is overfitting. Think about an investment model that has learned every tiny movement in historical data. It might look brilliant, the historical accuracy is high, the error is low. But what happens when the market regime changes? The model suddenly falls apart. Why? Because it didn't learn the underlying economic relationship. It learned some of the noise in the historical sample. A machine learning model should not simply memorize the training data. It should identify patterns that are useful when it encounters new observations. That's why professionals care so much about our ensemble performance. Let's start with something familiar: ordinary least square, or OLS. Try to choose coefficients that minimize the sum of square errors. In other words, make the model's predictions as close as possible to the actual observations. That's useful, but OLS has a problem. Suppose we have an enormous number of potential explanatory variables. OLS can potentially assign coefficients to many of them. Some may contain genuine predictive information, others may simply capture noise. Penalized regressions introduce a second consideration. Instead of asking only how well does the model fit the data, we ask how well does it fit the data after accounting for the model complexity. That's the key idea. For LASSO, we minimize two things simultaneously. First, the XXE. Second, penalties based on the absolute values of the regression coefficients. The objective can be written as SSE plus lambda times the sums of absolute value of the coefficients. So here, the lambda is the turning parameter, and this is one of the most important ideas to understand. If lambda equals 0, there is no penalty, so LASSO becomes equivalent to OLS. But as lambda increases, the model becomes increasingly reluctant to use large coefficients, and some coefficients can actually become exactly 0. That means LASSO doesn't merely string coefficients, it can effectively remove variables from the model. That's why LASSO is particularly useful for feature selections. Think about an analyst trying to predict corporate default. Suppose it starts with 100 potential variables. LASSO may determine that only 15 contribute enough predictive value to justify their inclusions. The remaining variables receive coefficient of 0, so the model becomes simpler and potentially more robust out of sample. So for example, image bank want to estimate the probability that a corporate borrower will default. Potential variables include D to E, interest coverage, current ratio, operating margins, cash flow, and so on. Instead of manually deciding which variable to keep, the analyst can also use LASSO, LASSO. The algorithm evaluates the trade-off. If adding a variable reduces the predictions error enough to justify the additional complexity, it stays. If not, its coefficients may be pushed toward 0. This is particularly valuable when analysts have many potential predictors. Now let's move from regression to classifications. Suppose we want to classify company into two groups: likely default versus likely not default, or perhaps positive sentiment versus negative sentiment. A support vector machines or SVMs is a supervised learning algorithm designed to separate observations into categories. Here's the intuitions. Imagine you had to group of observations plot on the graph. The job is to draw a boundary between them. There may be many possible boundaries, but SVM asks a more sophisticated questions. Can we find the boundary that separate the group while creating the largest possible margin between them? That margins matters. The observations closest to the boundary are particularly important. These are called the support vector. Support data can be separated with a straight line. Then we have linear SVM. In a two-dimensional example, that boundary is the line. In higher dimensions, it becomes hyperplane. If you have n features, the observations can be represented in an n-dimensional feature space. This separating boundaries is an n-1 dimensional hyperplane. You don't need to memorize the geometry for intuitions. The important point is simple. SVM serve for additions boundary that separate class while maximize the margins. So, but here the problems: real-world financial data is messy. Very few datasets have the perfectly separable. You may have financially healthy company that happens to look risky on a few variable, or a distressed company that temporarily looks healthy. If we demand perfect classifications, the model can become too rigid. That's where the distinctions between hard margin and soft margin become important. A hard margin SVM item to separate the two classes perfectly. No classification error are allowed. That sounds attractive, but in real-world data, it can be dangerous. Because forcing perfect separations can make the model excessively sensitive to unusual observations. A short margin SVM allows some observations to violate the margins or even be misclassified. Those violations receive a penalty, so the model balances two objects, create a wide margins but also keep classification error low. There is another distinction you need to understand: linear versus non-linear SVM. A linear SVM works when the class can be separated reasonably when using a linear boundary. But suppose the observations form a much more complicated patterns. A straight line don't work. That's where non-linear SVM methods become useful. The algorithm can construct more flexible decisions boundary to distinguish between classes. The benefits is greater flexibility, the cost is greater complexity. Now let's use a completely different idea. Suppose I give you a new company and want to classify it as either higher credit risk or low credit risk. One simple approach is to look at the company that are most similar to it. This is the intuitions behind the K nearest neighbor. The algorithm follows the three basic steps. First, choose a value for K. Second, identify the K observations in the training sample that are closest to the new observations. And third, classify the new observations according to the majority class among those neighbors. Now let's move to one of the more intuitive machine learning techniques: classification and regression tree, or CART. Think of CART as a decision-making flowchart. You start with one question: is step 2 EBITDA below 4? If yes, go left. If no, go right. Then ask another question: is interest coverage above 5? And continue. Eventually, you reach a final node containing the predictions. This is why decision trees are so intuitive. They resemble the way humans often make decisions. CAT can handle two types of predictions. If the target variable is categorical, we use the classification tree. If the target is continuous, we use a regression tree. But decision trees have a weakness. If we allow a tree to keep splitting indefinitely, it can become extremely complicated. Eventually, the tree can start describing peculiarities of training data rather than general relationship. That's overfitting again. So we need to control the tree. We can impose constraints such as maximum tree depth, maximum number of decision nodes, or we can prune branches that contribute relatively little explanatory or predictive value. The object is to not create the largest tree possible. One of CAT's biggest advantages is interpretability. It may presenting an investment model to a client. It's much easier to explain. If leverage is above the level and interest coverage is below that level, the company falls into the high risk categories. That decision tree, but contrast. So machine learning algorithm can be much harder to interpret. This is why decision tree can be valuable when explainability matters. In finance, CART can be used for fraud detections, equity selection, fixed income selections. Now we arrive at a very important idea. What if one model isn't enough? Instead of trusting one model, why not combine several? That's the basic idea behind ensemble learning. Think about investment research. Suppose 5 analysts independently estimate whether a company is likely to outperform. One analyst focuses on valuation, another focuses on momentum, another focuses on macroeconomic conditions. Instead of choose one analyst, we combine their informations, that the intuitions behind an example. Multiple models contribute to one final predictions. There are two important ways to construct an example. The first is example heterogeneous learners. That means we combine different types of algorithms. For classification, this can be done through a voting classifier. The model effectively vote. The class receiving the strongest overall support become the final predictions. The second approach is homogeneous learning. Here we use the same type of algorithm repeatedly but train each model using different samples of data. One important technique here is bagging or bootstrap aggregating. Here's the intuition behind bagging. Start with original training dataset and create multiple bootstrap samples. Each sample is drawn with replacement. That means the sample observations can appear multiple times in a particular sample, while another observations might not appear at all. They train the same type of model on each sample. Finally, combine their predictions. Why does this help? Because each model sees a somewhat different version of the data, so the model makes somewhat different errors. Combining them can reduce the influence of any single model mistake. This is particularly useful when individual models are unstable. So a random forest is essentially an example of decision trees, but there is an important twist. Random forests introduce randomness into 2 dimensions. For different subset of observations are used to construct individual trees. Second, a random subset of features is considered when building the trees. So instead of building one giant decision tree, we build many different trees. Each tree produce a predictions, then we aggregate those predictions. For classification, we generally use majority voting. For regressions, we generally use averagings. This is the central architecture of random forest. So let's walk through it carefully. Step 1, select a subset of observations and features. Step 2, build a decision tree using the sample. Step 3, repeat the process many times. Each tree produces its own predictions. Step 4, combine the result. For classification, majority voting. For regressions, average the predictions. The result is random forest predictions. Thanks for watching.